Hello everyone, today we are going to explain the network layer, data link layer, and physical layer. Previously we mentioned that the application layer generates data, and when it reaches our transport layer, it gets encapsulated. This means that on the outside we will identify its source port, destination port, and a series of parameters. No, this is an encapsulation at our transport layer. Besides encapsulating ports, we mentioned two very important protocols here. One is TCP and the other is UDP. One is reliable transmission and the other is unreliable transmission. For instance, when we are transferring files, we want it to be more reliable. But when we are doing video calls, we hope that the transmission speed will be faster, and the requirement for transmission reliability is not as high. After all, if we're on a voice call and there's a lag on your end, you can just repeat what you said in the next second. So, the reliability requirement isn't that high. In this context, in the future, we also need to identify, besides the port, do I need to specify where this data should be sent? To which person globally should it be sent? What is the person's name? In this process, our network layer is responsible for sending data from one host to another. In this process, we provide what is called an IP address. This provides a logical address for our network devices, allowing our routers to forward data packets based on routing. Common network layer protocols include IPv4, IPv6, SMP, and IGMP. Let's first take a look here. For example, what is our network layer, and what does its workflow look like? When our IP address is used as a network layer protocol, both parties need to have an IP address to identify themselves. Just like we all have our own names now, I am Teacher Boya, and everyone has their own name, like Jack or Rose. So, what form does the IP address take in this context? It certainly doesn't just come randomly. It is a 32-bit binary number. So, what is a binary number? Sometimes it might sound confusing to everyone. Let me tell you. Binary means carrying over when reaching 2, and the entire number consists only of zeros and ones. The number 2 cannot appear. Now I want to ask everyone if you see 1001 every day, can you understand it? We say this looks too complicated. So we choose to use decimal notation for IP addresses, which is what we usually use. What is decimal? It means the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's impossible to represent 10 with a single digit. To represent 10, we must first have a 1. A 0. So what about IP addresses? They are represented using dotted decimal notation, which means 4 groups of decimal numbers. In this context, each group of decimal numbers corresponds to 8 binary digits. That's why we often say it is 32-bit. This is an 8, this is an 8, this is an 8, and this is an 8. 4 times 8 equals 32. So here we say it's 32-bit. With each IP value, each group, each one separated by a decimal point. What about it? When converted, it becomes 8 binary digits. Among them, each group of numbers ranges from a minimum of 0 to a maximum of 255, separated by dots. Now here, when we receive data from the transport layer, at the network layer, we will encapsulate it further. Here is a piece of data, and outside, after passing through the transport layer, I will deepen the encapsulation. The original port, this is the encapsulation of the transport layer. We use a port to replace it, and once we reach the third layer, we will add a network layer encapsulation, using IP to replace it. Here, we also refer to this as an IP header. We place the source IP address and the destination IP address into our header. The so-called source IP address means who I am, what my IP address is, and the destination IP means whose IP address I want to access. Then, in between each router. Each network device maintains a table called a routing table, which is our route table. This table, like a map, guides the forwarding of our IP packets. So if I have it, I forward it to you according to the table. For example, if it receives a packet and it needs to go to network A, it will go out through my J001 interface, and I can send it to you. For instance, in this router, it is like this. This 000, it will record it. So you want to go to the network, you need to go out through my 000. At this point, I will send it to you according to this information. All devices work the same way. I follow this. I forward it to you using the routing table. Here, each router checks its own routing table. And finally, multiple routers help forward it step by step to the destination. And what about the destination device? It then decides whether to receive the data packet and processes it. How does the router in the middle learn this? How do our routers know which interface the other side is using to go through? At this point, we rely on our routing protocols such as OSPF or ISIS, which we will learn about later. These protocols help determine this to help our routers build the routing table. But here, I have a question for everyone. If a packet is sent to my RTE and I don't have this entry, what will happen then? Sorry, if I have it, I will help you forward it. But if I don't, sorry, I can only discard this packet, which means when it reaches me, I will drop it because I don't know where the destination is. Only if it's in my routing table will I help you forward it. So in this context, this is the workflow of our network layer. Besides the network layer, it also goes through a layer 2 encapsulation. So, what is layer 2? We say layer 2 is the data link layer, which is located between our network layer and our physical layer, providing some services for our network layer protocols like IP and IPv6. Here, we usually refer to layer 2 data as frames. But it doesn't matter whether it's called a frame, a packet, or a data segment. They all essentially refer to data. In this context, it is situated between the network layer and the physical layer to provide precise positioning on a link, for example, between one device and another. Common protocols include Ethernet, among others. So how is it transmitted here? For instance, during this process, I mentioned that all devices are connected to a switch. Now, if the PC's network interface complies with the Ethernet standard, then typically the broadcast domain corresponds to our IP subnet and our MAC address. It corresponds to identifying where you are on this layer 2 link, like which position you are on me. For instance, as we previously exemplified, if I want to find someone nationwide or globally, I rely on their name. But if I want to locate them precisely, I need to know which country, city, and place they are in. So how do I create an identifier here? Just like everyone has an ID card in their own country, here the ID card is the MAC address. Do we need to configure this MAC address ourselves? Not necessarily, as long as when it leaves the factory, that is, when it is being manufactured in the factory. A MAC address will be burned into its chip and it is globally unique and non-repeating. This MAC address is used to identify a physical device within our current network. It operates at the data link layer. And within this context, when a switch receives it, it will refer to the MAC address table, which contains a mapping of interfaces to MAC addresses. From which interface did I receive the MAC address, and what is it? For example, if the MAC address is AA, and I receive it on the J001 interface, I will record that the MAC address AA corresponds to the 001 interface in my MAC address table. Then, using the MAC address table, we guide the forwarding of our data. For example, if you want to find out who the destination MAC is, and the source MAC is AA, and you want to find DD, I will know that DD is connected to, say, the J003 interface below, and I will send it out to you. Now, during this process, when it reaches switch B will also check its own table. For example, here it is 001, and in its MAC address table, it remembers that 001 corresponds to DD, so I will help you forward it all the way. The MAC address itself definitely doesn't change. The ones I wrote here, like AA or DE, what about them? It is a group composed of 6 hexadecimal numbers made up of characters and colons. For example, here you have 4, 8, A4, 72. In this way, once our MAC address data reaches the physical layer, our physical layer will convert our digital signals into optical signals, electrical signals, or electromagnetic wave signals based on our transmission medium. Here, we call this layer of data a bit stream, but it doesn't matter. We refer to all of these as our data. The physical layer now is at the lowest level of the OSI or TCP/IP model. It standardizes aspects such as cables, pins, voltage, or interface standards. Common methods for data transmission include twisted pair cables, which we also call network cables, optical fibers, or electromagnetic waves. For instance, the network cable is something everyone should be familiar with, as shown in the first image on the top left. Here we have twisted pair cables, which are the most commonly used transmission medium for everyday internet access in businesses or throughout the entire network. Based on their ability to resist electromagnetic interference, they can be divided into several categories. One type is called STP, or shielded twisted pair, which is wrapped with a material similar to aluminum. In addition to this, there is also UTP. Of course, the price of STP is definitely much higher than that of UTP more because it has a stronger interference resistance. Besides this, we sometimes also categorize them as Category 5 or Category 6 cables. If it's a Category 6 cable, it has a cross-shaped framework inside. When we use network cables, making network cables is actually one of the most basic skills for a network engineer. To make a network cable, we need to arrange the wires according to the wiring sequence, and then insert them into the RJ45 connector, pressing them tightly with a crimping tool. The wiring sequences are divided into T568B and T568A, with T568B being the most commonly used now. Its wiring sequence is white-orange, orange, white-green, blue, white-blue, green, white-brown, brown. Why don't we use network cables in all environments? It's because its transmission distance is too short, only 100 meters. If it exceeds 100 meters, it won't immediately disconnect, but during this process, the signal will attenuate and be affected, which is why optical fiber was developed. Optical fiber has a longer transmission distance, but optical fiber is also categorized. Firstly, it is divided into single mode and multi-mode. Single mode is suitable for long-distance transmission, and we can often see the SM label on it. If it is multi-mode, it is labeled MM, then this is an optical module. We need to insert the optical fiber into the optical module and then insert the optical module into an optical port of a switch or router to establish a connection. As for optical fibers, we cannot bend them arbitrarily because they are not like our network cables. Inside network cables, there are copper wires, and bending them doesn't have much impact. However, inside optical fibers, there are glass fibers used to transmit light. So, if you bend them at a sharp angle, it could potentially prevent the light from passing through. The optical module converts our electrical signals into optical signals to generate light signals. Within this context, optical modules can be distinguished by SM, single mode, or MM, multi-mode. For optical fibers, besides the SM, MM markings, we can also differentiate them by the color of the fiber. If it's yellow, it's mostly single-mode fiber. If it's orange, aqua, blue, or black, it's often multi-mode fiber. Now, in this process, there's the serial port cable below. Actually, it is mainly used in wide area networks, and the type of interface connected to this serial cable varies according to the wide area network line. These types include synchronous serial interfaces or ATM interfaces, which are used relatively less. Besides these three types, we say this is limited, and there's also wireless. Wireless signals can be transmitted through electromagnetic waves. For example, Wi-Fi signals allow us to obtain data through these electromagnetic waves. The above is a simple description of our network layer, data link layer, and physical layer. If you want to learn Huawei certification technology or want to obtain the Huawei certification question bank, please send me a private message, or you can leave more comments below the video.